going to do a quick review of some of our integration methods. In number 1, hopefully you'll see a very simple integration by substitution, since the denominator is going to be the chain rule of the numerator. So we've often done this with fractions, where we pull them apart so that we recognize the chain rule. So many of you no longer have to show this substitution, but what you're thinking of is that our u value is inverse sine. So when we differentiated that, we would get 1 over the square root of 1 minus x squared. And then remember that we moved this du, we multiplied both sides to move the du or the dx over to this side. So now what we want to look for in our integral is this du value, and right there it is. So this was what facilitated our substitution method, and then we wanted to find the u value, and right there it is. So this substitution made our integral very simple to solve. So the integral of u du is now just a power rule. Raise the exponent to 2, divide by it, add a constant. And then all we had to remember to do was our back substitution. Here we have an inverse sine squared, so I'll leave the exponent out here so it doesn't get confused with the inverse symbol. All right, so number 2 is very similar, except that it is a definite integral. But we notice that we have an expression inside a square root, so that would be a good possibility to be our u expression. And then our du value here would be 0 on the 1 and 8t. And then remember that here it's not a dx but a dt. So now we know what this 2t is there for. If we move it over here, it's going to be contributing to our du value. So if we rewrite this, and again, you don't need to show these steps. There's different ways of thinking of this. But what we really want here is for this to be an 8t dt. So if you think of a 4, we can see that there's going to have to be a 1/4 on the outside of the integral. And then we can write this as u to the 1/2. And here's our du value. So now we'll have 1/4 of, and a power rule, add 1, divide by the new exponent. And the thing that we haven't taken care of along the way here is what to do with our limits. So originally here it would be correct to say that these values were going to be substituted into the variable t. Well, in our next step that isn't going to work, since we've now converted to u. So we're going to take this value of 0 and we're going to substitute it into our expression to convert it to the value u. So if we put 0 in for t, we'll get 1 plus 0. And then we're going to do the same thing with our value of negative 1. Let me not cross that out there. How about if I use a highlighter? I want to take this negative 1 and substitute it in here for t. And that will give us a 1 plus 4. So now we actually have our limits in reverse order. So you could, if you want to rewrite this and put a negative sign out in front, but that will be taken care of when we do our evaluation here. So when we multiply these, the 2 cancel with the 4, so I'm going to write 1/6. And then I'm going to substitute 1 into the u, 1 to any power, and then I'm going to put 5 in. So you can leave that as 5 to the 3/2, or you could write its equivalent, cubing 5 and then taking the square root. We could bring a 5 to the outside. So either one of those values would be fine. All right, question 3 is that same process with a definite integral, but it's in multiple choice form. So you're given a very nice simple hint that tells you here that to evaluate this integral, we are going to let our substitution value be 3x plus 1. So exactly the same process we just did a minute ago. If this is our expression for u, then we know that our du value would be the derivative 3 dx. So we need to find this in our integral. So let's rewrite our integral then. So this can be rewritten as our f of u, and then we needed to insert to get that 3 there. I don't want to actually write it there because I'm already doing the substitution. Let me erase, but I'm actually thinking of putting that 3 there to get du. So if I inserted a 3, then that's really 1/3 of du. All right, and then our last problem, think of what we did a minute ago. We have to convert these limits. So the 2 and the 0 no longer apply. So now we have to substitute those. And where do we put them? We put them right here into our step that tells us how to convert values of x into values of u. So we put a 2 in, and we will come up with a 7. And we put a 0 in for x, and we will come up with a 1. So it looks like our best choice here is choice D. So remember to convert the limits. So we have to get a proper value of du, and we had to convert limits here to be very careful. All right, completing the square. If we looked at this, we'd say, well, substitution wouldn't work because if I let this denominator be our u value, then the du would have to have a 2x, and there's no variable x. So we know that u du substitution wouldn't work for this problem. So the hint here that we're going to set this up to complete the square. Remember, we want to make this a perfect square trinomial. So we are simply going to use your algebra and make this a perfect square, and you'll see how nicely that will work in a second here. So we take half of the middle coefficient, so we're going to add a 9, let's say plus sign, and of course do no harm, so we'll subtract 9 so that we haven't changed our expression. And now this is going to look like, I hope you'll see that pretty quickly, that it's going to look like the form of our inverse tangent integral. So I would like this numerator to be a 1, so I'm going to move that 3 to the outside. And then we're going to think of this. You can look at the top of your paper. I reminded you of that formula here. This looks like a u squared plus an a squared if a is the square root of 2. So this is going to become 3 times our 1 over a value inverse tangent of u over a. And then we have a plus c. All right, and one more long division example. Again, if you tried doing a u du substitution, you could see that we'd have trouble. The denominator doesn't have an x squared, and the derivative of the numerator would need a 3x squared term. So you could try substitution method, but it wouldn't work. So you might be given a hint like you are here. So when the degree of the numerator is larger, then rather than completing the square, our long division method would be the likely candidate. So we're going to divide by x plus 2. So we'll have an x cubed plus 2x squared, and then don't forget that we are subtracting. And then we'll have a negative 5, so we'll have a negative 5, a negative 5x, how about that? Negative 5x squared, and then a minus 10x, and we're subtracting, so we would have a 14x, and then we can add here a 0 in the constant column because we can divide one more time here. So 14x plus 28. So our remainder is a negative 28. So remember that the remainder goes over that divisor. So now we can think of this integral, and now our first 3 terms are simply going to be power rule. And then our last term, we're going to think of that. Looks like it's going to be a logarithm term. And and we'll talk about that here in a second. So antiderivative, so this would be a 1/3 x cubed, and the next term will be a negative 5/2 x squared and a 14x. And now let's take a little detour here and think about this last term here. If we think about this as an integral, what if I brought the 28 to the outside here? Do you see that a u/du substitution, or a du value, would simply be 1 dx? So you don't actually have to write this here. Hopefully you'll see that this is going to be the natural log of x squared, but don't forget that we have this 28 term here, so that is outside as a coefficient. And then we'll put absolute value there and our constant of integration. So it looks like a monster answer, but it was really quite simple.